Hey, and welcome back to Anton Math. Now in sections 6.5 and 6.6, we're going to be working on solving triangles that are not right triangles. So with right triangles, we know we can always use SOHCAHTOA to very quickly and easily solve these triangles, and we can use inverse trig functions to quickly find the angles. But for non-right triangles, this becomes a little bit more tricky. The first thing that we need to note is that to solve a triangle, we need at least 3 pieces of information. Now that can be any 3 pieces of information, and by pieces I mean either angles or sides. So as long as I have 3 angles or 3 sides, or a combination of those, we can solve the triangle, with the exception of if I only have 3 angles, we cannot solve the sides. Only having the 3 angles will give us infinitely many possible solutions for those sides. But let's take a look at all the different combinations of triangles that we could have. Let's consider these following 4 cases. We could have one side and 2 angles, and that could either be in the form of a side between 2 angles or a side followed by 2 angles, and we call that an ASA or an SAA triangle respectively. We could also have what we call an SSA triangle. That's where we have 2 consecutive sides where the angle is opposite one of those sides. This is our triangle number 2 here, and you can see the solid lines and the solid angles, those are my known information. The dotted lines are the sides that I do not know. Now 3 is when we have 2 sides and an included angle. We call that an SAS triangle. And then for 4, that's when we have 3 sides. Now triangles 1 and 2 are solved using what we call the law of sines, which we're going to learn in this video. And we're going to focus on this, on these 2 first. Our next video will be working on this first type of triangle, and then in 2 videos from now we're going to be working on the second type of triangle. And we'll jump into these case 3 and 4 once we get to section 6.6. So first, let's take a look at what we mean by the law of sines. The law of sines says that in any triangle, triangle ABC, we have the following relationship. That sine of the angle A over the side A is equal to sine of the angle B over the side B is equal to sine of the angle C over the side C. We see here we've drawn our triangle with our conventional notation, where the little letters, the lowercase letters, are used to designate the sides, and the uppercase letters are used to designate the angles, and we always draw our triangle so that the side A is opposite the angle A, side B is opposite angle B, side C is opposite angle C. So in other words, we're saying we can take the ratio of the sine values at any of these angles in my triangle over the length of the opposite side, and it's going to be equal to the sine value of any other angle in the triangle over the length of the opposite side. Now how do we know this is true? What's the proof for this? Well, it's a fairly simple proof. Recall that the area of the triangle here, so I'll write A sub t like we did in our area video. Recall that this is 1/2 AB sine theta, where theta is the angle between the sides A and B. Now in this triangle, that could be 1/2 BC sine A, or we could write this as 1/2 AC sine B, or we could write this as 1/2 AB sine C. Right? These are all going to give me the area of my triangle. The area doesn't change depending on which angle we use, so these are all equal to each other. Now if I multiply by 2 over ABC to all of these, if I multiply through on all sides of this identity by 2 over ABC, here the B and C will cancel, and I'll get sine A over A. Here the AC and 1/2 will cancel, I'll get sine B over B, and here I'll get sine C over C, exactly what we have here. Okay, so that's very simple proof using the area formula we have for the triangle. So because the area is the same, we see that these proportions will all be the same. So that's the introduction to the law of sines. Now in the next video, we're going to apply this to those first cases that we looked at. where we have two angles and one side. We'll see you there.